Alright, the first thing to do would be to make a chart here and then check the voltage across the rectifier, bridge rectifier with the motor off, motor on, and with belt slip, and that's with no capacitor, no filter capacitor. And then after that, hook my oscilloscope up and check for ripple voltage with no capacitor, no filter capacitor, with the motor off, motor on, and with belt slip. That's coming up next. Okay, I have four 3 amp transformers hooked in series here, and I have my voltmeter across the bridge rectifier, and I have my motor set up here on these wires here, ready to go. So we'll turn the voltmeter on now, and we'll plug in the transformers. Okay, I'm getting 52 volts now across the bridge rectifier with no load. I'll turn the motor on now. Okay, I'm getting 61, we'll call it 62 volts with the motor running. I'll record that. Motor on, 62 volts. Now I'm going to check for belt slip. I'm going to stall the motor here. .41 volts, I got belt slip. 41 volts, I got belt slip. Okay, now I'm set up to check ripple voltage. I have my oscilloscope connected directly across the bridge rectifier. And there's what I have right now. Power applied to the transformers and to the unregulated supply right now. And that's what I have right now for ripple voltage without the motor running. That's motor off. Alright, my oscilloscope is set at the 5 volt mark. Everything's calibrated here. I'm looking about 3.5, not quite 4, about 3.5 volts. That's peak to peak. So with motor off, that's 3.5 volts, it's about 3.5 volts peak to peak. Now we're going to check it for motor on. Okay, now I'm going to turn the motor on. And that's with the motor on. That is the ripple voltage of the motor on. That looks to be about 45 to 50 volts. We'll call it 50 volts peak to peak. Okay, no sense doing anything with belt slip because it's just way off scale. So that'll be undetermined right now. Okay, now I'm all set up to determine the motor current. Okay, with the motor running now, I'm using a series resistor here. And with the motor running, I have 214 millivolts. That's the voltage drop across the resistor, series resistor. The motor running. Now for belt slip. For belt slip, I need to check the voltage drop across resistor now. About 1.3 volts belt slip. Okay. I have one more test to do now, and that is take the voltage drop across the motor with the series resistance in the circuit. Okay, 63 volts, normal running conditions. 63 volts. Now I'm going to check it for belt slip. .40 volts on the belt slip. And that's all the data we need now. Okay, I took a measurement on the series resistance here. It says 0.56 ohms. It's about 0.5 to 0.6 ohms, so I'll just make it 0.6 ohms for the series resistance. I measured that before. Okay, now we're going to start solving for the current now. Under normal running conditions, motor running conditions, the voltage across the series resistor was 214 millivolts. So put 214 millivolts. And then we'll divide that by the resistance of 0.6 ohms divided by 0.6 ohms, and it gives us a current of about 356 milliamps under normal running conditions. 356 milliamps. That's under normal running conditions. Now under belt slip, Under belt slip, we had a voltage drop across the resistor of 1.3 volts. 1.3 volts divided by, again, the 0.6 ohms. Divided by 0.6 ohms. And that's about 2.16 amps. Okay, there's our data for the current flowing through the motor under heavy loading conditions. Now we can just solve for the impedance across the motor under normal running conditions. Under normal running conditions, we had 63 volts dropped across the motor. 63 volts, will divide that by our series current under normal running conditions of 356 milliamps. And that gives us about 177 ohms. And that 177 ohms is the motor impedance. Now let's check the motor impedance under the condition of belt slip. We have 2.16 amps flowing. The motor drops to 40 volts. So 40 volts across the motor on belt slip divided by 2.16 amps. And the impedance drops down to about 18 ohms. So we drop to 18 ohms impedance. Again, motor impedance. So what we're looking for is trying to look for a worst case scenario of when the motor is going to be close to a stall where the belt is slipping. When the belt is slipping, that's going to be about the maximum where I'm going to let off the pressure and let the voltage build back up and everything on the motor when I'm doing any kind of machining. So if I hear belt slip, I level off the pressure a little bit. So with that belt slip, I'm looking about roughly around 18 ohms motor impedance. And that's very important to work with now when it comes to designing the regulators and the filter capacitors and stuff like that for the rest of the circuitry now. That's a very important number right there. Okay, let's get on with the rest of the design here now and get on with some calculations for the filter capacitance for the supply voltage that's going to be needed to run this. Okay, here's something I never thought about. Whenever I put my ohm meter on the motor windings here, I get a reading here, but if I turn the shaft a little bit here, the motor resistance windings change. So as I keep on turning the motor, the resistance windings change. So that would explain why I'm not getting, say I'm down to 5 ohms there at that setting. So that's why it's more accurate to take the voltage drop across the motor, and I'm sorry, the voltage drop across the motor divided by the current by using that series resistance I was using to determine the current to get more of an accurate impedance measurement here.